This is a video going over the practice test that's been shared on Google Classroom. Okay, so this first video will go over the multiple choice section. The first question says the variation with time t of the acceleration a of an object is shown. We're given this graph. What is the change in velocity of the object from t equals 0 to t equals 6 seconds? So change in velocity can be determined from the area under the line for an acceleration time graph. So this first little bit has an area of 2. This rectangle here is 4 times 1, which is 4. And this one is half of 4 times 2, which is also 4. So the total here is 10 meters per second. Second question. Two blocks of masses m and 2m are traveling directly towards each other. Both are moving at the same constant speed v. The blocks collide and stick together. What is the total momentum of the system before and after the collision? Well, total momentum doesn't change during the collision, so whatever it is, it's got to be the same for both of them. So it cannot possibly be B or C. The total momentum before is plus 2mv, and this one is minus mv, so the total is plus mv, so it's got to be A. Okay, so this question says the graph shows the variation with time of the resultant net force acting on an object. The object has a mass of 1 kilogram and is initially at rest. What is the velocity of the object at a time of 200 milliseconds? Well, in a force time graph, we know that the area under the graph is the impulse or change in momentum. So, and we know that delta P is m delta V. And it was initially at rest, so delta V is going to be the final speed or final velocity. So what is delta P here? It is 1/2 times 200 times 10 to the minus 3, because that's milliseconds, times 80. So that's 100. Let's change it to 0.1. 0.1 times 80, which is 8 kilogram meters per second. And so delta V is equal to delta P over m. And m was 1 kilogram, which is 8 over 1. So it's 8 meters per second. A. Question 4. A ball is thrown vertically upwards. Air resistance is negligible. What is the variation with time t of the kinetic energy Ek of the ball? Okay, so Ek is equal to 1/2 mv squared. The decrease, so v is going to decrease to 0. It's going to start high. So it's got to be either A or D. So the kinetic energy starts off being big. V is squared, so it doesn't matter the direction. It should be positive both before and after. Or in fact, it could be B. It could be B. Because it has to start big. Okay, now, is it linear? So kinetic energy, the velocity decreases. So if it were velocity against time, it would look like A. But it's not velocity against time, it's a function of velocity squared, so it's going to look like D. It's going to be non-linear. Can I say anything to make that clearer? If you plot Ek against time, if you plot V against time, it would look like this. If you plot Ek against time, that should be a graph of v squared over time, because this first part is constant. So if we square this, we get the same, and it's gonna become a parabola instead. Okay, so D is the answer, and all the negative values here are going to become positive. An object has a weight of 6.10 times 10 to the 2, 610 newtons. What is the change in gravitational potential energy of the object when it moves through 8 meters vertically? Okay, so EP is equal to mgh, and mg is the 610 times 8, which is 4,800 plus 80 is 4,880 joules, or 4. Now I need to give it to the correct number of significant figures, which should be 2. So it's 4.9 times 10 to the 3 joules. That one. A boat with an output engine power of 15 kilowatts moves through water at a speed of 10 meters per second. What is the resistive force acting on the boat? Okay, so here it's moving at a constant speed, so we can use this equation P equals FV, where F is the resistive force. So P over V is the answer. So 15,000 is kilowatts over 10 gives us 1,500 newtons. 1.5 kilonewtons. An astronaut is moving at a constant velocity in the absence of a gravitational field when he throws a tool away from him. What is the effect of throwing the tool on the total kinetic energy of the astronaut and the tool, and the total momentum of the astronaut and the tool? Well, he's done work, so the kinetic energy is going to increase. So there's more movement afterwards than there was before. The second thing is the total momentum of the astronaut and the tool. It can't change because there are no external forces. So total momentum, it doesn't change, and the kinetic energy increases. It's got to be D. A table tennis ball of mass 3 grams is fired with a speed of 10 meters per second from a stationary toy gun of mass 0.6. The gun and ball are an isolated system. What is the recoil speed of the toy gun and the total momentum of the system immediately after the gun is fired? The total momentum of the system has got to be 0, so it's got to be one of these two. And we want the recoil speed of the toy gun. So mv bullet has got to be equal, m bullet v bullet, it's got to be equal to m gun v gun. So v gun, or negative, v gun is equal to m bullet v bullet over m gun. And the mass of the bullet was 3 grams. So that's 0.003 times the speed of the bullet, which was 10, over the mass of the gun, which is 600. So this is 0.03 over 600. So, oh, then it's not 600, it's 0.6. 0.6, there we go. So it's 0.05. So it is A. A compressed spring is used to launch an object along a horizontal frictionless surface. When the spring is compressed through a distance x and released, the object leaves the spring at speed v. What is the distance through which the spring must be compressed for the object to leave the spring at v over 2? Well, the energy conversion that's happening here is we have this Hooke's energy, or the elastic potential energy, that's being lost, and we have the kinetic energy, an equivalent amount, that's being gained. So the Hooke's energy is half kx squared, and that's got to be equal to 1/2 mv squared. So the elastic potential energy lost equals the kinetic energy gained. We can cancel the halves here. We can rearrange this for the original x. So you can see x is equal to square root m over k v. That's an expression for our original extension for releasing it at speed v. Now if we want to release it at speed v over 2, then we can rewrite it like this. We can go 1/2 k x prime squared is equal to 1/2 m v over 2 squared. And if we rearrange this for x prime, then we'll get an expression and we can compare them. So we cancel the halves again. We get x prime squared is equal to, well, let's write it like this. So k x prime squared is equal to mv squared over 4. And if we rearrange here, we get x prime squared is equal to m over 4k v squared. So x prime, so the new extension that we need for half the speed is going to be equal to the square root of m over 4k v. And that's the same thing as 1 over 2 times square root m over k times v. And you can see that x prime is equal to 1/2 of x, because it's changed by a factor of 1/2. Previously we didn't have a half there. And so it's exactly x over 2. 10. A motor of input power 160 watts. This is power. Raises a mass of 8 kilograms. That's mass. Vertically at a constant speed of 0.5 meters per second. What is the efficiency of the system? So basically the useful power out. So efficiency is useful P out over P in. Okay, and the useful power that we get out is mgh per second. So mgh over time. So it's mgv really. We can do it like this to make it a little bit clearer. We can do, I'm just going to try to make this as obvious as possible. So we go it's useful energy, E out, over total E in for every second, each second. So then we have mgh over 160 is the amount of energy being put in every second. So that's equal to 8 times, let's go roughly 10, times 0.50 over 160. So that's half of 80, that's 40 over 160, which is 0.25, 25%. Okay, so that's the multi-choice section. If you have any questions, bring them to class.